Thanks. Wow, this is an awesome workshop. I wish I was here for more of it, and I'm super nervous after today's awesome talks, but let's see how this goes. So I don't know some of you, so let me introduce myself. I have broad interests, probably too broad. I like to think about things like how clouds might reorganize over open oceans and demand rain band shifts on the one hand. I am motivated a lot by the regional scale water cycle effects that may go down in my kids' future on the other. And the interests intersect basically frequently on this issue of confronting turbulence. And I'm kind of obsessed with it. And I admit I'm in a bit of an engineering rut and feeling the pendulum swing. But the motivation for this talk and is very, very much aligned with the motivation for the Tapio presented. I'm really worried about low clouds. Feel like they should keep us up at night, the state of low clouds in climate projections, the importance of lower tropospheric mixing to macro scale climate change, etc. So as one video to summarize that, try parameterizing that. Like that's what happens off the coast of subtropical eastern boundary currents all the time. It's like, look at that soup of fractal reorganizations of open and closed forms of cellular convection. And how is that organization, that morphology, going to respond to the possible scenarios of aerosol changes and warming and subsidence changes? I think you could argue it's not parameterizable until you start to really resolve the cloud forming eddies that are operating across that sharp inversion. Or at least it seems like it when you look at it. We know a lot about these systems. We know how fundamental the details of the mixing underneath the cloud are and how they produce entrainment across the inversion. And we know that we can produce satisfying looking simulations of those cloud systems, as we've seen in many talks when we simulate a small patch of atmosphere with a lot of computational intensity for a short period of time, and we can produce things. We have been able to produce things for a decade, like the breakup of a parcel of air as it's advecting from colder to warmer waters, and which causes the whole system to become dimmer at top of atmosphere as you stare down on the top of it. And we know if processes like that, if there's analogs for processes like that with global warming, that will be coupled to much more complex climate forcings associated with aerosols and other things, and dynamics and dynamical interactions between this brightness and the ITCZ, et cetera, that's going to matter to our experience of regional water cycles. So that's the motivation, is like these details of turbulence matter. They matter on planetary scales, they matter to the regional water cycle. So then on the other hand, where do we stand in global modeling? Well, it's changing, which is great. Tapio's talk was super inspiring. But in terms of like uniform grid global simulations, this is the state of the art. It's really exciting. We can simulate we can cover the planet with a 1 kilometer mesh. You might be tempted to think that what you see off the coast of California and Peru there resembles what we saw in the satellite observations. But we should caution ourselves that no, that's nowhere close. These kilometer scale global models are wonderful for simulating explicitly for the first time the interactions between the largest eddies and the largest macro scale storm systems, deep convection and broader climate dynamics. But for the low cloud forming eddies, you just add up the grid resolution, and it's easily tens of thousands. I buy hundreds of thousands or millions of times more computationally expensive. Yeah, so that's the challenge. Where we stand in global modeling is really unsatisfying. Most of these important boundary layer processes occur at these 100-meter or below scales, computational intensity octuples for resolution doubling. We're stuck at about 1 kilometer. We have higher order methods to sort of draw moments and parameterize the sub-kilometer regimes, spatial coherence and complexity, but those are mathematically cumbersome and hard to imagine generalizing, and inevitably need to be trained on some limited LES data. And besides the point, any well-intentioned parameterization can fail in circumstances that this designer didn't anticipate. So like it's a reason to worry, right? A little bit. Okay, so in this context, I'm sort of captivated and have been by 10 or 15 years now probably with MMFs, multi-scale modeling frameworks, which are just a funny way to simulate the atmosphere where you strategically kind of find a way to embed higher resolution physics you didn't think you could afford by limiting them to small patches of atmosphere that are idealized, two-dimensional, periodic. You draw some assumptions, and then you hope that nonetheless, this little patch of explicit convection that has high resolution can be extrapolated, and its macro scale statistics, its coarse grained behavior in time and space can interact in a way with broader climate dynamics that's a valid proxy for the missing physics that seem unaffordable. So this business is experiencing a bit of a renaissance inside the DOE as it's been ported to GPU supercomputers. Here's a figure from Walter Hanna at Lawrence Livermore Lab, just kind of showing that the way this works is kind of, you should envision like tens of thousands, or these days as many as 1 million little cloud resolving models embedded inside of the planetary model. The cloud resolving models have short time steps. They resolve eddies. They, then they interact with each other on 30-minute and longer time scales through their mutual influence on the host climate model grid. And we can get some essence of cloud radiative feedback that's a little more explicit. And in the past 10, 15 years, this was a way to map out in advance some of the lessons that have been confirmed in fully uniform global storm resolving models, like the dynamics of the Madden-Julian oscillation ahead of schedule. But of course, now global storm resolving models handle that much more elegantly. But in the coming decade, especially in the petascale GPU era, I think this same MMF technology is really promising for penetrating this stubborn boundary layer frontier. Just trying to bridge the gap between large eddy simulations and global climate models. In free running simulations, not calibrated, but just the same tension of trying to bridge that gap. One example from my own group is just a silly first attempt at this that tries to take the usual kind of 100-kilometer scale coarse resolution global CAM, and instead of embedding a classical superparameterization that has this storm resolving 4-kilometer resolution that can resolve mesoscale convective systems and huge deep clouds, just kind of change the grid structure that's embedded, spend another 100 times more computing power to embed a lot of vertical resolution and horizontal resolution to just begin to resolve the outer scales of boundary layer turbulence, so that at least it's not grid scale eddies doing the job of forming your low clouds. A start, right? A start. And it's been a few years, and we're finally able to do some short simulations that reveal what this does to the overall aerosol cloud indirect effect. And some interesting things happen, like a regime dependence. So the orange dots here are what the storm resolving resolution says the aerosol cloud liquefaction due to industrial loading should be. And the blue dots are what this eddy permitting version does. Might look like the mean is kind of similar, ironically, but behind the mean, these triangles are showing you that there's a regime dependence emerging between the raining clouds and the non-raining clouds. And that's sort of something we know about in observations in LES simulations is different physics mediating the mean. It's a different representation of aerosol cloud indirect effects. So, and this is evolving, we're starting to build ways to regionalize this so that not using like really principled techniques of like thinking about uncertainty and where to deploy LES resolution, but at least geographically say, embed the LES resolution where it matters. Okay. So yeah, but I guess I kind of come from this world where I think as we look at multi-model emulators of CMIP simulations, we should worry about the lack of global model biodiversity in those simulations. And I think that's healthy to have more biodiversity. Okay, so this says, there's a bunch of things happening. Exploding national GPU-based supercomputers, porting of MMF cloud resolving models to GPU that's buying orders of magnitude increase in computing savings that might help us modify our view of low cloud and turbulence mediated feedbacks. Okay. All right, but this is a machine learning conference, right? Okay, so this is the other half of the dilemma. Like maybe we can use machine learning parameterization to get to sub-kilometer scales. And that'll be the rest of this talk. So I think it's really exciting because it might have breakthrough potential. Global climate models can make creative complexity trade-offs between the computing available and the degree of complexity we choose to represent on the convective scale. But usually that's constrained by a really hard job, simulating the whole atmosphere for decades, many times, to get statistics on scenario planning. And that limits me, for instance, when I use multi-scale modeling frameworks, to unsatisfyingly coarse resolution, only the outer scales of boundary turbulence, small domains that can't seamlessly produce transitions between shallow and deep systems, etc., right? And the exciting thing about machine learning parameterization is that the job could really radically change to just producing short simulations that are going to be mined for their essence with emulators. And that means that, you know, right away we can do more justice to turbulence physics. We could do something more LES-like on global scales, three-dimensional, higher resolution, larger domains. And that's the reason I'm interested. And so I'll share some of my vantage point from trying to do this work in the context of these superparameterized simulations. And I want to first draw a comparison to coarse graining. So this is, you know, arguably much more physical training data to use for machine learning parameterization. You know, the results of one of these global storm resolving models where there's no strange scale separation being drawn in the data itself. It's naturally continuous, although you do have to draw one after the fact, right? So that might mean that the simulation itself doesn't contain clean information on what's needed to correct a coarse resolution model. I think doing machine learning on MMF output is interesting because you have these arteries already in the simulation that was used to produce the training data, these low dimensional arteries that naturally produce a predictor-corrector relationship on a coarse timescale of 30 minutes between the average properties of this convection and the planetary scale dynamics. And so those are nice low dimensional arteries you can hone in on for machine learning. But the disadvantage, of course, is a totally artificial scale separation that someone has drawn in a model. And right, but it's convenient because it removes some causal ambiguities that sometimes happen in coarse graining simulations, especially when you coarsen in time, because these are positively relevant arteries. So it's sort of a complementary playground to understand some of the trade-offs that happen with architectures or other aspects of machine learning that sidestep these complexities of coarse graining. Now, let me be straight up that what I'm going to show you is, at this stage of the field, a super crude, archaic brute force attack on the problem. So what I mean is that the inputs I'm going to be feeding to the neural network are macro scale thermodynamic properties like the temperature profile of the host planetary model that didn't know about convection, its moisture profile, some incoming fluxes, surface pressures, and sunlight. And the architecture is going to be super crude. It's going to be just a dumb sheet of neurons, you know, a deep feed-forward neural network. And the outputs are also going to be really macro scale. They're going to mix together all kinds of processes: convective heating, latent heating, radiative heating, basically the entire physics package. So the vertical profile of convective heating, vertical profile of moistening, precipitation rates, and radiative fluxes. Okay. And I didn't think that would work 3 or 4 years ago, but then there's this one result that's provoked me ever since. Stefan Rasp came to visit UCI 3 years ago or something. And we worked for a while and got this result. So we eventually, you know, basically the way this works is you treat the problem as local in space and time. You run a benchmark simulation. You produce 10 to 100 million training samples from each latitude and longitude and time coordinate of a kind of homogeneous aquaplanet simulation. You flatten that vector, and then you've got these pairs of inputs and outputs. And you know, there's so many samples that you can even use a deep neural network, and you never find the overfitting limit. And in this one case, we managed to take the resulting neural network, plug it back into the host model, and the coupled interaction actually worked to the extent that it didn't drift, and it produced the same wave spectrum as the model it was trained on, but 10 or 20 times faster. Yeah, that result has stuck with me. It got me really interested in the dream. Like maybe we can do this. But in hindsight, this has been very finicky and empirical, and it's very difficult to reproduce that result in even modestly more complicated settings. Testament to the fact that this is far from operationally reliable. This is what frequently happens when you plug one of these brute force crude emulators into the model. It just blows up spectacularly in the mid latitudes within a day or two. So, the problem is that these reliably, reproducibly skillful stable emulators, there might be example of one or two of them here or there, but they're not reproducible yet. So, but I think there are some lessons emerging that are worth trying to distill right now. And so I'm going to focus the rest of this talk on some do's and don'ts that I'm collecting of personal interest. And, big caveat, I won't be surprised at all if in 1 or 2 years that list is completely different, because this stuff is changing so fast. Okay, so don't do what I do. I guess do try to avoid brute force. And I think the result that really speaks to me is this beautiful result from this year, Yuval, O'Gorman, and Hill. So this is coming from one of those coarse-grained simulations, a hypsometric aquaplanet, statistically steady, but it's sort of the definition of feature engineering, the opposite of brute force. It's going in as an MIT-trained atmospheric scientist, going into the guts of a cloud-resolving model and extracting all the things you should extract if you want to really be right about physical constraints, extracting mass condensation rates and making those the target so that the heating and the moistening associated with the condensation process is consistent across variables, separating vertical diffusion from other processes so you can force downgradient constraints, and doing the machine learning at the time step level so you're not jumbling up processes and you can use different neural networks to handle different regimes. And the results are beautiful. This is the same neural network, the same mean rainfall for the aquaplanet, and the same PDF of rainfall. It's really an exquisite result. It's the result of years of hard work and careful thinking about the architecture. So I guess the association is do separately emulate separate processes if you want to enforce constraints. I suspect that's the secret to the success of this approach. So here's one neural network here that's predicting things like the tendency of mass due to physical tendencies from which we derive the heating versus the moistening tendencies. And a separate neural network down here that receives the surface fluxes and diffuses them and has therefore the luxury to enforce a downgradient constraint. It's like beautiful planning here. And a ton of work. You have to go into the guts of a cloud resolving model and extract all of these process rates if you want to do this kind of thing. It's not easily approachable. But corollary, don't coarse grain in time. That's what I did originally. It's tempting, big speed ups to be bought there. But you can only separately emulate separate processes from a cloud resolving model if you stick to the time scale of its individual integration circuit, I think. Here's another example of a remarkably stable emulator of something really hard that I never succeeded in doing, which is to separately emulate microphysical rates. I've, in previous work, avoided emulating microphysical kind of, liquid generation, ice generation profiles because it's so darn hard. Just sidestepped it and tried to predict their thermal consequences instead. That's how we got the Raspadal result. But here's an example of how to do it. A successful emulation of a warm rain bin microphysics scheme that begins with classifiers that separate different regimes and train multiple dedicated regressors for those different processes. Another example, I think, of the importance of separately emulating separate processes. Do enforce column physical constraints, of course. So these data-driven methods can easily leak 50 to 100 watts per meter squared in a column, unless you tell them otherwise. How else would they know? Two ways to tell them. You can just use the Lagrange multiplier to draw your constraints, conserve column radiation and mass and water. But there's a trade-off there between the accuracy, which you need to get reliable prognostic skill, and the constraint, which you actually need to be meticulous. And so a better approach that Tom Buechler convinced me just works, and there's a nice recipe for how to do it, quite general. Just put the hard constraint in the architecture, and that seems easy enough to do. So why shouldn't we? But what are the trade-offs? You might ask, does the hard constraint hurt your accuracy? It's another thing that has to be learned. Maybe it's harder to get down gradient when you have this constraint. Doesn't look like it though. So the truth here, this is a tropical mean heating profile from a holdout data set from an aquaplanet. The unconstrained networks in blue, amidst the typical spread of the fit, there's equal, it's like the same quality fit, loss constrained, architecture constrained. Okay. But, this one is leaking machine precision amounts of mass and energy, which is important in the column. But don't expect the satisfying constraints are going to buy you generalization. So this is exposing the same neural network to a 4 Kelvin warmer climate state that it wasn't trained on. And you can see relative to the truth that all the networks, the unconstrained one, the architecture constrained one, they're just wildly failing in that test. And maybe the roots of prognostic errors have to do with this inputs going out of sample and similar issues of extrapolation danger. Do continue to use physics then to do obvious things like just strategically normalize your inputs and outputs. So this is a fun paper that we should have the preprint coming out very soon, and kind of the culmination of a lot of work that Tom Buechler did during his postdoc the last couple of years. But the idea is really simple: just avoid extrapolation error by using physics to normalize your inputs and outputs. So don't use specific humidities, which are obviously unbounded due to Clausius-Clapeyron in different climates. You do use relative humidities instead because they are always relatively bounded. There's all kinds of mappings you can do to rescale your inputs so that the PDFs will align across climates, or at least align more, or a lot more. And so I think for moisture, we'll use relative humidity. For temperature, after some testing, we'll use like the Nealon-Ahmed kind of buoyancy metric. That's a good predictor for convection. You can also do this for the latent heat fluxes and sensible heat fluxes. And here's a result I really enjoy from that work. So the usual brute force neural networks trained on their holdout data validation set look like this. Tom, I think these intercomparisons are great. Tom's comparing aquaplanet SPChem to a real geography SPChem to the hydrostatic SAM. You can see kind of similar patterns of errors in the holdout validation. Warm the climate by 8 Kelvin in this case, and yeah, of course, you've got massive errors in the tropics where you have warmer temperatures than have ever been seen by a lot. But if you just physically rescale the inputs and outputs upstream of everything, then you don't have nearly as much of this problem. And that's a dramatic climate shift, right? 8 Kelvin. We have no idea what that does to prognostic stability so far, but it seems like an obvious thing to test. Do always look at your neural networks and hunt for their physical credibility, right? It can be hard. I was talking to Chris Brotherton about this to articulate the full list of physical credibility tests you need. You can often assume there's one that should tell you everything and be surprised that you should have looked at another. So this is probably a place where we all need to agree on a list that's sufficient. But one that I thought was really interesting in this latest work on finding climate invariant neural networks is this analog to the convective linear response matrix, where you just sort of use a Schaap feature and fortune matrix to figure out your neural network sensitivity. So for instance, of the input here, you have moistening coming in from the bottom to the top of the atmosphere, temperature coming in, and this is the moistening rate, the output of the neural network to those inputs. So you see a lot of action on the diagonal because convection tends to mix moisture deposited at one level vertically adjacent. But what should be surprising in this graph is that you see a ton of off-diagonal action, and that's evidence of major problems in the neural network fit. It thinks that really non-local processes are important for convection, which maybe for radiation, for the temperature, for the heating field, since there's radiative things, but not for the moistening rate. And what you'll see after just the simple physical renormalization is like a much more satisfying localization towards a diagonal. And I think the last point I want to make is do explore industrial scale hyperparameter tuning. That's a lesson I learned from working with computer scientists. We're like, hey, let us look at your data. We'll let a GPU crank on it for a week the way we normally do. And so we got a whole family of neural networks, and they had really different offline validation skill. That's the color field here. Okay, so holdout validation loss all over the place. Some of them were much better than ones we'd ever trained ourselves, just allowing the GPU to scan over different neural network widths and depths and sizes and loss rates. And then the important thing is to take that entire family of neural networks and plug them in online and ask them to feedback with the host climate model. And the y-axis here shows you the resulting error relative to a benchmark simulation. It's a log scale. So just look at the spread. so many of these neural network coupled GCMs just skyrocket to unphysical attractors. They might seem to run for a long time, but in completely the wrong basic state. And even for the ones that appear to be good, the tail of this hyperparameter fit, the blue colors here, you can see orders of magnitude difference. So on the one hand, this offline skill doesn't seem to be a great reliable predictor of the online performance. On the other hand, I don't think it's a coincidence that the most skillful model in that hyperparameter search is the one and only neural network that achieved Raspadal kind of errors and solved our reproducibility in this case. Thanks. So please do report, if you can, these spread statistics. I think I'm personally missing so much information about what goes wrong when we perform our human hyperparameter tuning process. I feel like it's like I can't, there's so many claims being made about what matters, like, oh, ResNet really matters, or having separate neural networks for the heating and the moistening really matters. But I'm missing the information about the spread for each of those architectures, the space of sampling hyperparameters. And yeah, I think it's really hard to tell what matters because of that. But I guess I think these questions about reproducibility and reliability and controlling instabilities have suffered barriers that are just dumb software engineering. It's hard to tune lots of neural networks without spending a lot of time. Translating neural networks into Fortran kernels is annoying. And that's been changing. There's new software. Pick your favorite hyperparameter tuning package. I hear Keras Tuner can deploy itself across GPUs in ways that backfill Slurm queues conveniently. And Fortran Carrots Bridge is one option. This PyTorch thing seems awesome. But either way, find a way to test dozens of these neural networks in prognostic mode so we can see the spread and challenge our assumptions about what's really important architecturally. So yeah, you can download that if you want. Okay, but to summarize, I really think machine learning parameterization is super exciting. It really might have breakthrough potential. Shiny results do exist, more coming out every year. But I feel we still don't have reliably reproducible ways to make stable emulators. If I was an operational agency, I'd be rightfully skeptical, especially for this full soup of coupled processes. That would be the dream. So I'm uncertain, but interested still. I think some emerging machine learning lessons, do's and don'ts. Do separately emulate physical processes, but the corollary is don't coarse grain in time. I actually have cognitive dissonance about this, and it came up in our lunch discussion. Part of me still feels like we should coarse grain in time. I'd love for us to talk about this. There's good reasons to do both, but the Yuval result is really sticking with me, and I feel like that's its secret sauce. And some of the stuff about the symmetries you can require of Navier-Stokes only makes sense to apply at the fast timescale level as well, not before the soup of eddies has mixed itself. Do enforce column constraints, why not? It's easy, but don't expect the constraints to buy you generalization. Do try to do obvious things to your inputs and outputs using your climate physics knowledge to get that generalization. I guess we haven't done enough of that. And let's explore industrial scale hyperparameter tuning. Why do we limit I limit my imagination to what fits on one GPU, but I feel like I'm living in the dark ages, like when MPI was invented and we only did fluid dynamics for things that fit on one processor. And maybe that's just me. But yeah, I guess I'm really curious. And again, this is a snapshot in time. If Stefan Hoyer manages to make a differentiable primitive equation solver that allows us to actually optimize on the coupled loss function, like the landscape could completely bifurcate and I wouldn't be surprised. Anyway, I think this is really interesting. Thanks for letting me dump my disorganized thoughts about it. And thanks to all these people. Oops, where are they? Oh yeah, so yeah, I'm definitely excited about this. To Tapio's point about reductionism, this is my version of it. It's explicit calculations we trust from the inelastic equations enabled by amazing developments in GPU computing. And there's a lot we can do there right now. I'm also excited by this, but I've got a lot of question marks. And yes, yeah, and then it's a privilege to show all these people's work. Thanks for your time.
Thank you, Mike. That was great. Any questions from one? Thank you. I didn't even have to ask. Make sure the line, yes, thank you.
Hey, Mike, it's Maria. Great talk. You shouldn't have been nervous. You were excellent. I have a question about one of the do's that you presented, and I've seen Tom talk about this before, and I actually asked him this question too, but I'm curious about the next step, which is like its solution, which is the do about using our physical knowledge for normalizing or standardizing our input variables into neural networks, or using that as a physical constraint for, let's say, climate change. And so the example that you have used is relative humidity. And so I understand how that works in the tropics, but I don't understand how that would work in the subtropical latitudes, right? Because we have relative humidity depending on temperature, your diurnal cycle. This presents issues for things like severe convective storms. So I was just curious about that. You know, how do you hope to generalize some of these input normalizations that you use for your grid cells across different regions?
I see. Yes, I think, oh, that's a good question. I think like there's two issues there that I'd like to separate. I think for this chronic issue of models just blowing up, the biggest instability staring us in the face is in the tropics. You can easily go out of sample there. On the temperature side, it's the hottest place of the planet. Water vapor goes exponential, and then all of your inputs are corrupted. And so I think protecting yourself from that with relative humidity is great. To your question about like climate invariance of low cloud feedback, including the details of all the organization of the low clouds I was trying to motivate things with. Yeah, my view is that the only way that my hope of the dream there would be that you could, actually train on multiple climates, but short samples of them, explicitly generated climates, and just you're sort of investing in your faith that the LES, despite the short sampling time, is giving you something learnable that you could then use in to untangle some interesting dynamical feedbacks associated with the convective organization changes across climates. Did I answer your question?
Yep, thank
Okay.
you. Yeah. And I'll bother you later.
Okay, cool.
Mike.
Hi, I second that. Great talk. I was wondering if you considered adding on your do list, looking at sort of post-hoc explainability of whether or not the predictions that your neural network, like why it's coming to those, makes sense to you physically. And it sort of goes a little bit hand in hand with Yanni's work, and I discussed this briefly with Noah as well. I was wondering how you think about this, because it's one of the things that's sort of missing from the lineup, as far as I see it.
Yeah, so I don't have a good answer for you. I was provoked for a long time when we got the first fit. 70% variance explained by a neural network. It's like, how can this be? There's information about a convection parameterization hiding in here. The fact that a sheet of neurons can get this level of fit might tell me something about how to parameterize convection. I feel ill-equipped to interrogate the neural network beyond obvious things like the convective linear response metrics that you get from its tangent, or the Schaap feature matrix I showed you, or I mean, we've glanced at those, but I can't say that I know how to untangle some revelation about how to make a cartoon model that emulated what the neural network did, because the neural network is really overfitting, like Tapio said. It's a bunch of geometric transformations that happen to add up to this scale, supported by some regularization to try to control the problems associated with that. But the issue of interpretability, I feel my pendulum swinging away from this low dimensional engineering work towards a different aspect more in your world that I think is really interesting. Like, so much of this engineering work is going to be happening in large centers and SDCs and NOAA, et cetera. But there's this other category of work that's just from the overwhelming quantity of output we can get from storm resolving simulations, which is interesting in its own right, which we can be clustering and trying to find latent spaces of to interpret. And my interest in that dimension of machine learning is growing rapidly. But that's the kind of understanding work I want to do more. I want to look at, the latent space of microphysics turbulence interactions and stuff like that.
Sounds awesome.
Cool.
One of your do's, which you didn't put on your summary, I like very much, which is report the failures.
Yes.
How? I mean, the journals won't take
Yeah.
those papers unless there's a positive result too. So,
Well, it takes work, so it's annoying, right? But so does running an ensemble of weather forecasts instead of one. Everyone hates a case study paper, but we take faith in like a ensemble spread. And but the associated work, I feel like, is not as bad as it used to be, because we have this like PyTorch Fortran library that you can, and we have auto tuning libraries. Like Keras Tuner is really friendly. You know, it doesn't take much time to go. You know, it's easy to get tens of thousands of GPU hours from our national computing infrastructure if we ask for it. It's pretty easy, it seems, to run Keras Tuner to sample a bunch of architectures. And then I think it's just incumbent upon us to really expose all of those architectures to the couple of situations we inevitably care about. Because otherwise, we're just writing about stuff that's maybe irrelevant to the operational situation. Is that what you were asking, or that's kind of
you were talking about, please show us what didn't work, and I think you just asked the question about how to automate sort of massive hypertuning problems.
right? I think usually one does that.
You may not even succeed. Find any network that works, and those should also be reported.
Interesting.
Those are,
okay.
Having 2 years of postdoc work not actually get anywhere is actually worth knowing that approach didn't work. So that's a different problem, maybe.
Yeah. Well, we need to, as a community, like value these negative results, I guess, if we want to know about them.
That goes beyond machine learning.
It's so empirical and anecdotal that, like, otherwise we're just discovering it in the hallway, and I don't know what to say.
Stefan.
Hi, Mike. Thanks for the really interesting talk. I had a question about you talked about hyperparameter tuning, or like the difference between like the loss during training and sort of like the online performance. I guess I'm wondering how much of that do you think is the different architectures, or just that you like retrained a new neural network with like different random weights? I'm wondering if like we did try just we found often retraining the same model architecture multiple times get very different performance.
I don't think it's that. So, you know, we've tried to control the instabilities by training a family of neural networks with different random seeds and coupling to their average. And you maybe buy a little bit of time in the instability. But I really think the more chronic instability is just from ignoring Clausius-Clapeyron and allowing your temperatures to have the possibility of going out of sample in ways that exponentially amplify vapor tendencies, and then everything goes haywire. I think you control that with a simple renormalization of your input, and you get the first big step. But I think there's lots of other things after that. Honestly, we just haven't sampled this hardly at all. And yeah, but did I kind of answer your question? Like, yeah.
I guess well, I guess specifically, like, I mean, obviously there's a lot of clear improvements you could make, but in terms of like, the model doesn't work well. Sometimes that's just like chance instead of like bad architecture.
Right. Yes. Yes, that's true. I think it's another reason that we should be always doing these in ensembles, where we sample over the intrinsic spread of fits, because you have an easy chance of missing something. But I think I also think we know something in our work that that controlling the input humidity gives you a major effect on your initial prognostic instability that I think we can rationalize. But I wouldn't be surprised if there's lots of other secondary effects associated with details of the architecture that also, I think we just need to sample the heck out of this stuff. And you know, we have the clusters to do it, but I just kind of don't know what's possible. What an interesting time.
Any other questions online?
But if brute force hyperparameter tuning is this effective, like in this dinosaur kind of two-stage process we currently live with, what's it going to do when we can actually optimize on the coupled error? So like a differentiable model that we can deploy that hyperparameter tuning machinery on the actual coupled error. Sort of a wide open question that's really interesting.
Any other comments? I saw somebody get up and then they sat down and now they're getting up again. Thank you, Robert.
What are your failures? I wanted to come back to this question of reporting your failures. So one thing I know is that Alistair and Mike and I have all been editors for this journal, James, at various points. And if I think of getting a paper at James that says, well, we tried all this stuff and it didn't work, I'm not sure. I accept that there'll be some subset of people that'd be interested in that, but that'd be a small subset.
Yeah.
The criteria, you'll remember is like, what did we learn? Right.
Mm-hmm.
And so I think that one of the things that I've struggled with, I accept that there's a ton of empiricism in a lot of the ML stuff, in terms of what architecture is best, and there's clearly a lot of subjective choices. But I think that's what we would need to be able to articulate. What did we learn about this approach? It's not enough to say it failed. What you need to be able to articulate is why.
Right. Yeah, no, I agree. I think it would be hollow and not very interesting to just show a failure. I guess what I'm trying to say is that we need more than just a success. If there's a claim that a success was enabled by a particular architecture, a decision to split a neural network or couple it with conditioners or normalize inputs, it needs to be demonstrated, with the accompanying information about the spread of possibilities in the vicinity of that architecture associated with reasonable hyperparameter scans. It's like, do the distributions overlap or not? What's our burden of evidence to support claims like that? And are we agreeing? Cool.
Yes. Okay, any other comments? I think I'm going to do a change over to online. Thank you very much, Mike. And one more round of applause, please. Thank you. And I see that Aditi is there. And you saw that we do have an audience, right?
Kind of.
We shouted you earlier, yes.
There they are.
I'm sorry. I'm guessing that we caught you when you stepped away.